Hi guys. Hi. My name's Alice, and I'm the social and marketing sec of MathSoc. So, MathSoc. How many of you have heard of MathSoc? Okay, not a lot, admittedly. How many of you have heard of a MathSoc event? I see those hands, yeah. And how many of you have been to one? You came! So, thing is, I've got to admit, MathSoc has been pretty rubbish this year. And, I think that's a real shame, because we don't have, a sense of community in maths. I think when people come into maths, they kind of form friendship groups, and you don't really extend outside those friendship groups. And I think that's just such a shame, because they're people from many different backgrounds, languages, cultures. You get the idea. So I thought I'd change that. What I thought I'd do is I'm going to set up a movie night in the Roscoe Theatre. I'm going to get the big lecture theatre, going to get everyone there, and I'm going to have sort of like an interactive movie night. You can come in comfortable clothes and just chill, and I can guarantee that you will meet someone new, step outside your comfort zone a little bit, and get to know more people on maths. And I think that'd be really good and just increasing, when you walk into the Alan Turing building, I don't think you really know anyone when you walk in there, and I want to create that sense of knowing people. So that's my aim in this. So I'm going to ask those 3 questions again. Who here has heard of MathSoc? I just said it, guys. Seriously? And who here has heard of one of our events? Movie night 2 weeks from now? Anyway, so I look forward to seeing lots of you there. I'm going to send out emails, flyers, and there's a Facebook event. One last thing that I want to say that's unrelated to MathSoc. I understand the freedom of speech, and I think it's really important to express your opinions. However, when you go out of your way to say something extremely rude to someone, that's not freedom of expression, that is abuse, that is bullying. And I'm talking specifically about the week 3 feedback. If you really don't like this lecture, and you really don't like this course, whoever that was, then why are you here? I think we are being taught by such, a kind, a smart, really encouraging, approachable and friendly man, and Sarlis has not put me up to this. I'm saying this on my own, and many second and third year and fourth year students agree with me on this. So, moral of the story is, if you've got something bad to say, or if you've got problems of your own, don't take it out on innocent people, because that's really not cool, guys. Okay, thank you. And also, can we have a round of applause for Sarah Lees?
I think thank you for all your comments. I think, the Math Society is a big thing. So if you can get involved and be part of it, please try to do so. Okay? All right. Now, I don't want to I just want to recap what I did yesterday, right? This is maximum likelihood estimation. We talked about 2 different methods yesterday, you guys remember. One was the standard approach for finding the MLAs, and the second one was the The second one was the indicator function approach for finding the MLEs. Right, I did a couple of examples, well, one example on this and a couple of examples on this. Now, before I go ahead, let me do one more example. Let me do one more example on the indicator function approach, because I'm not sure whether all of you got what I meant by the indicator function approach, right? This is one of the examples from the booklet. All right, so the question is to find the MLE of delta. Now, you can try out the standard approach first, right? So the likelihood function, because there is only one parameter, delta, likelihood is a function of delta. All right? This is what you get, right? This is the likelihood function, okay? Taking the log, you get n delta minus take the derivative, you get n, right? Set this equal to 0, doesn't mean anything. All right? So when you use the standard approach for finding the MLEs, you are going nowhere with it, right? Because you come up with this equation that n equal to 0. All right? So in this case, the next step is to try to use the next step is to try to use the indicator function approach, right? So you rewrite the likelihood as the product of the density function. All right? But remember, you should go back to the definition here, guys. I don't know whether you can see this. No. You should go back over here, guys. It says that x must be greater than or equal to delta. So you must specify the condition that the indicator function containing the condition that xi is greater than or equal to delta. Yes? All right. Now, if you simplify this, guys, you get E of n delta minus sum sorry, x. Okay. Now, what you have here is a product of indicator functions. You should look at what I gave you yesterday, guys. You probably remember the rules I mentioned to you yesterday in the lectures. Let me show you those rules if I have them here. Sorry. Not this one, no. Just give me a sec, guys. Yeah, remember these rules, guys. These are the three rules I mentioned. These are the three, 1, 2, 3, are the rules I mentioned in the class yesterday, or in the lecture yesterday, for simplifying products of indicator functions. So this product here will simplify to do you see this, guys? That this product of indicator function will simplify to the indicator function, the delta is less than or equal to the min of xi. That's using the second rule, right? Is that clear, guys? Yeah? Yeah, all right. Right, so that's only part of the procedure for indicator function. Now, let me take this away, guys. The next thing I'm going to do, we need to do, I'm not good in drawing, as you can see. We need to draw the likelihood function, L of delta versus delta. So we need to draw this function as a function of delta. Now suppose this is your point where corresponding to the min of xi, right? How do you think the graph will look like, guys? If I draw this on this axis, how do you think it will look like, guys? It's not rocket science, guys. This is not rocket science. So it will look like this. And do you see why, guys? Because when delta is less than the min, this is equal to 1 by the definition of indicator. Now, but this function here, you have exponential of n delta. Now, n is a positive constant. So as delta increases, n delta is going to increase. So what you have is you have an increasing function. Are you guys with me? You have an increasing function when delta is less than or equal to the min of xi. And when delta is greater than min of xi, this condition is no longer satisfied, and therefore it is 0. So the whole function, the entire function, is equal to 0 when delta is greater than the min of xi. Is that clear, guys, or no? Some of you seem lost. It's just plotting of functions, guys. You should have done, I'm not being patriotic, but this is kind of stuff you did in Calculus 1. Right, the largest point of the graph is this one, right? Hence, the MLE for delta is equal to the min of xi. Sorry, guys. Is that clear, guys, or not? So I know if you have problems with this, guys, you need to just do more examples and get familiarized. As you know, you learn things by doing examples. So any questions before I move on? Your eyes good? You okay, guys? Yeah. Okay. All right, so I've done already three examples on the use of the indicator function approach. Now, you will use the indicator function approach whenever the standard approach does not work, right? In other words, you get weird solutions, weird-looking solutions. Using the standard approach. So in that case, you can use the indicator function approach. Okay. All right, guys. Now, here we are. Next one. All right. The next one is called the restricted domain approach. Yeah. This is different from the two approaches I talked about so far, the standard approach and the indicator function approach. Right. Now it works like this. What it does is, suppose all right. And so you have a random sample from from a joint density function given by this fx semicolon theta. And we are assuming that the parameter theta has a conditioning like this: theta greater than theta 0, where theta 0 is a fixed non-constant. Now, in this case, if you want to find the MLE of theta, then you need to follow what is known as the restricted domain approach, right? So if you get a question like this, you need to follow this approach, which I'm going to describe in a minute, all right? The first thing you do is so the first step is this, guys, is to find the MLE of theta by the standard approach, ignoring the condition that theta is greater than theta 0. The second step is if this condition is satisfied, guys, then right, if the condition that theta hat is greater than theta 0 is satisfied, then the MLE of theta is theta hat. If the condition is not satisfied, right, that is, if theta hat is less than theta 0, then right? So if the condition is not satisfied, then you plot the likelihood function over the range from theta 0 to infinity. Yeah? Okay. And the fourth step is, guys, the fourth step is find all right, these are the 4 steps. I mean, I know maybe some of you, it looks like jargon, I don't know. But I know as I start doing some examples, this will become clearer, I hope. So these 4 steps are is the procedure that you need to follow for the restricted domain approach. So a restricted domain approach is where you have a random sample from a distribution, but you have a condition. You have a condition on the parameter theta, a condition like this. So in such cases, you have to use what is known as the restricted domain approach. You need to follow this. You need to follow these four steps. All right, let me do some examples. I know because looking at this, it looks like a lot of procedures. So let me do some examples to make what I have written here clear, right? So let's look at one example, guys, where you can use the restricted domain approach. So suppose this is an example where you need to. This is an example where you need to use the restricted domain approach, right? Can you see what I've written, guys? You have a random sample from an exponential distribution with parameter lambda, but you also have the condition that lambda must be greater than 1. Okay? So you have a condition on the parameter lambda. And the question is to find the MLE of lambda, right? All right, so the first thing to do is to write down if you look over here, guys, is to find the MLE of theta by the standard approach, ignoring the condition, right? So that's what I'm going to do first, guys. I'm gonna find the MLE for lambda, ignoring the condition that lambda is greater than 1. Okay. All right. So this is the likelihood function. Now, do you guys remember the standard approach? What's the next step in the standard approach, guys? Let me check your memory, guys. What's the next approach? Yeah, good. Yeah, you take the log. Exactly. So you take the log of this guy, which is and then you differentiate the log set this to 0. I solve this equation for lambda, which is n right, which is excuse me. So this is the solution for this equation. Now, to make sure that this is an MLE, you need to do I know we did this before, guys, but All right. So lambda hat, guys, is an MLE. All right. Now, what I have done here is to ignore the condition that lambda is greater than 1 and find the MLE. That's the first step here, it says here. The second step, if theta hat is greater than this, then the MLE of theta is theta hat. So what it says is, let me put this here, guys. If theta hat, which, sorry, not theta here, it's lambda. If lambda hat, which is 1 over x bar, is greater than 1, right? If it's greater than 1, then the MLE of lambda is 1 over x bar. Right? That's the step number 2, right, in the procedure I gave you guys. If you just look back here, guys. If theta h is greater than this, yeah, then MLE of theta is this. Okay. Now, if if lambda hat is less than 1, right, then you cannot say the same thing, right? So in this case, if lambda hat is less than 1, you need to plot L of lambda as a function of lambda. Now I know you guys are all experts in plotting graphs. Now, so what I'm going to do, I'm going to draw a picture. My pictures are never good, really. I'm going to draw a picture here, guys, of L of lambda on the y-axis, lambda on the x-axis, and I'm going to plot it over the range from 1 to infinity. Yeah. So because the range, remember, we are assuming that lambda is greater than 1. So we don't care about lambda less than 1 because we want to minimize, right? Okay. Now, if you plot this, guys, how do you think it will look like? I mean, here, this is the function, guys. This is the function. If you plot this function versus lambda, how do you think it will look like? It will look like this is where I wish I could teach you calculus, but I'm not here to do that. So no, I'm not here to teach you guys calculus. So how do you think it will look like? If you plot this function here versus lambda, when lambda hat, which is 1 over x bar, is less than 1, it will, I can tell you, it will look like I'm not gonna explain to you now because I mean I think you should do some homework on plotting graphs, guys. Right? So the graph will look something like this. Yeah? You agree with me or not? Just try plotting it, guys. I'm sure you've done enough of this before. Yeah? If you plot L of lambda versus lambda over the range from 1 to infinity, it will look something like this. Now, what is the largest point here? What is the largest? The largest point of the graph is at lambda equal to 1, exactly. So this implies that lambda hat is equal to 1. All right, so to summarize what we have done in this example, I would say, so the summary is as follows. The summary sorry guys, if lambda hat, so if one or x bar is greater than or equal to 1, right, then lambda hat is 1 over divided by x bar, right? This is if 1 divided by x bar is less than 1, yeah, then lambda hat is equal to 1. Because this is the summary. Is that, some of you seem lost. You guys okay or what? Just try plotting these functions, guys. You know where I got these graphs from. So there are two answers to these questions. If 1 divided by x bar is greater than or equal to 1, then the MLE for lambda is 1 divided by x bar. And if it's less than 1, then the MLE for lambda is 1. All right? So this is how you would do a question like when you have a question, a restricted domain, that is, the parameter theta has a restriction on the possible values it can take. All right? So in this case, the parameter lambda must take values greater than 1, which is a restriction, right? Okay. Any questions, guys? Just when you have free time, just try and see how I got this graph, guys. I want, right? Try and see how I got the graph, guys. All right. All right. Now, those are the three. So basically, just to summarize, kind of, guys. There are three approaches. There are three approaches for finding the MLE of theta in the scalar case, right? One is the standard approach. So the standard approach is where you write down the likelihood function, take the log, differentiate the log, set it equal to 0, solve the equation, and finally you make sure that the second order derivative is less than 0, right? So that's known as the standard approach. The second one is the indicator function approach. Here you use the indicator function approach if the standard approach does not work. In other words, it gives weird answers, all right? If it gives weird answers, you use the you use the indicator function approach, guys, right? And the third one is the restricted domain approach. This is where the parameter of interest is restricted to a certain subset of the real line, right? Like, say, lambda greater than 1 or something, yeah? So in that case, you use the restricted domain approach. So these are three approaches you can use. I mean, in the exam, in the exam, I will not tell you which approach to use. It's something you need to figure out. Like in the test, in the in-class test, or in the exam, you need to figure out by yourself which of the three approaches is most appropriate to use. And that's why it's really, really, really important that you do lots and lots of examples, guys. Once you do enough examples, you will know which approach will work and which will not work, right? Okay? Okay, so, yeah. All right, so that's kind of a summary of, it's kind of a summary for the scalar case. Now, let's see, I haven't done any examples on the non-scalar case. Okay, so let's do some. Right, I mean, so far, all the examples I did so far are for the scalar case, right? That is, the distribution has only one parameter. Yeah. Now, I'm going to do some examples. All right, so this is the famous example where you have a random sample from a normal distribution which has two parameters, as you know, and find the MLAs of the two parameters, right? Okay, so the first thing to do here, guys, in this case, the likelihood is a function of two parameters, right? Okay. Is that right, guys? This is, I'm sure you guys recognize this one. This is the density function of the normal distribution, guys. Yeah? Now, if you simplify this, guys, you get right? You just simplify this, you get this, right? Now, excuse me. Once again, I think I've mentioned this many times already. It's really, really, really important that you know how to simplify products of functions, right, to this. Because over the years I've been teaching this course, I've seen the most common problem is with simplification of likelihood functions. And many students can't do it correctly. Yeah, that is to get from this line to this line, right? It's really important. If you look in the course website, You know the course website, right? Yeah. There's a node called elementary math or something. It gives you some hints on how to simplify products of functions. So if you go to the course, to my course website, you will see there's a link that helps you how to simplify products of functions, right? Yeah. So this is the likelihood. The next one, right? This is the log of the likelihood function. Now, because we have two parameters, right, you need to find the partial derivatives, right? So the first, I'm going to find the partial derivative with respect to mu, which will be all right, this is the partial derivative with respect to mu. You can simplify this a little bit, guys. So you get right? So this simplifies to this, guys. All right, the next one, you need to find the partial derivative with respect to sigma. So it will be all right, this is the, yeah, this is the partial derivative with respect to sigma, right? Call this, set this to 0, call this equation 1, set this to 0, call this equation 2. I'm going to put this over here, guys. Hopefully you can see this. Next, I'm going to solve equation 1. Equation 1 implies that the sum of right, which implies so the solution for equation 1 is equal to that mu hat. The estimator for mu is equal to the sample mean x bar, right? Now equation 2 implies that I'm going to replace mu by the estimator for mu, which which we just got here. All right, so this is the MLE for sigma squared, and this is the MLE for mu, right? This is the MLE for sigma squared, and this is the MLE for mu. Now, in principle, you will need to check that whether these are MLEs by working out the second order derivatives, but they can be very lengthy. So when you have more than one parameter, I will not expect you to find the second order derivatives and show that they are MLEs. So like in this case, it is sufficient to say that these are the MLEs for mu and sigma. Okay? So there's no need to find the second order derivatives. All right, guys, I'll see you guys tomorrow. Any questions about the course, feel free to send me an email, right? Yeah, I know. I should have said. Sorry about it. Yeah, sorry. Yeah. It should have been greater than or equal to 1.